Good afternoon, everyone. I am Latero B. Sereno, and for today's video, we're going to discuss the multiplicative functions, the Euler-PHI functions, and the sum and the number of divisors. And our objectives for today's video, at the end of the lessons, the students should be able to prove theorems on multiplicative functions, use appropriate theorems in determining the values of the Euler-PHI function, number of divisor, and the sum of the divisors functions. Conduct a mathematical investigation on selected arithmetic functions using ICT tools and research. So what is Euler-PHI function? So Euler-PHI function or the Euler's theorem, it was already discussed by the team of Sankala. And we will just recall the Euler-PHI functions. When we say Euler-PHI functions, or it is also called the Euler-Twoshins functions, it is a function that counts the numbers of the positive integers less than n that are co-prime to n. And it is written to the P of n. And P of n, the P of n, it is the number of the non-negative integers less than n that are relatively prime to n. In other words, that n is less than to 1, then P of n is the number of the elements. For example, we will going to find the phi of 9. So phi of 9, number that less than 9 are 1, 2, 3, 4, 5, 6, 7, and 8. So the number the phi of 9 has the prime, relatively prime, which is the 6. It has 6 relatively prime to the phi of 9. So what is arithmetic functions? An arithmetic functions f is called multiplicative if the functions f of mn is equal to f of n, f of n. Whenever that m and n are relatively prime positive integers, or let's just say the greatest common divisor. So we have the example. Let's say that the functions f of n is equal to 1 for all n is a multiplicative because f of mn is equal to 1. Otong i-separate para masabtan. So f of m1, f of m is equal to 1 times f of n is equal to 1. So that f of mn is equal to f of n and f of n, where m and n are the greatest common divisor. These multiplicative functions or this property is called the completely multiplicative functions. So we have another example. So let's say that the functions f of ab is equal to 1. Say f of ab is equal to 1. Let us separate. So f of a is equal to 1 multiplies to f of b is equal to 1. Then f of ab is equal to f of a multiplies to f of b, where a and b are relatively prime integers or the greatest common divisor. So we have the theorem 1. So if f is a multiplicative functions and if n is equal to p sub 1 raised to a sub 1, p sub 2 raised to a sub 2, all the way to the p sub s raised to a sub s is the prime factorization of the positive integer n, then the functions f of n is equal to f multiplies to p sub 1 a raised to a sub 1 multiplies to f p sub 2 raised to a sub 2 all the way to the f of the p sub s raised to a sub s. So let us prove this statement. Since we have f is a multiplicative and p sub 1 raised to a sub 1, p sub 2 raised to a sub 2, all the way to the p sub s raised to a sub s is equal to 1. We see that the functions f of n is equal to f of p sub 1 raised to a sub 1, p sub 2 raised to a sub 2, all the way to the p sub s raised to a sub s is equal to f of p sub 1 raised to a sub 1 multiplies to p sub 2 raised to a sub 2 all the way to the p sub s is equal to a sub s is equal to f of p sub 1 is equal to a sub 1 and f of p sub 2 raised to a sub 2 and p sub 3 raised to a sub 3 all the way to the functions p sub s raised to a sub s. Since that the p sub 2 p sub 2 is raised to a sub 2 and p sub 3 raised to a sub 3 all the way to the p sub s raised to a sub s is equal to 1. We know that these functions f of p sub 2 raised to a sub 2, p sub 3 raised to a sub 3 all the way to the p sub s raised to a sub s is equal to f of p sub 2 raised to a sub 2 multiplies to the f of p sub 3 raised to a sub 3 all the way to the p sub s and a sub s, so that the functions f of n is equal to p sub 1 raised to a sub 1 multiplies to f of p sub 2 raised to a sub 2 multiply to the functions f of p sub 3 raised to a sub 3 all the way to the p sub s raised to a sub s. And this is the continuing, and we find that the functions f of n is equal to the p sub 1 raised to a sub 1, functions p sub 2 raised to a sub 2, and the functions f p sub 3 raised to a sub 3 all the way to the functions f of p sub s raised to a sub s. And this is, we considered its values, its prime, and this is at prime powers. So we have the theorem 2. If p is prime, then phi of p is equal to p minus 1. Conversely, that if p is a positive integers with phi of p is equal to p minus 1, then p is a prime. So let's say that we have the example that p is equal to 5. So phi of 5 is equal to 5 minus 1, so it is equal to 4. So phi of 5 is equal to 4. And we know that the 5 is a prime number. Then we have the second example. Let's say that we have the p is equal to 9, and we know that 9 is a composite because it has 6 factors. It has 6 factors of 9. These are the positive and negative 1, positive and negative 3, and the positive and negative 9. So it has 6 factors. So we have the p of 9 is equal to 9 minus 1. It is equals to 8. So let us prove that if the p is prime, then every positive integer that less than p is relatively prime to p, since there are p minus 1 such that integers that we have phi of p is equal to p minus 1. That's the example that we have in example 1, that p is equal to 5, that 5 is a prime number. Let's say that the p now is composite. So we have the p of 9, the second example, and this is explanations. Conversely, that if p is a composite, then p has a divisor d, where d or the divisor is less than 1 but greater than p. And of course, p and d are not relatively prime because p sa itong second example nga p of 9 kuan siya kanang composite number siya. Since we know that at least one of the p minus 1 integers 1 to such that p minus 1, namely that d is not relatively prime to p, or p of p is greater than or equal to p minus 2. Hence, that if p or phi of p is equal to phi minus 1, then p must be prime. And we now find the value of PhiFunctions at is a prime powers. So we are now in the theorem 3. So in the theorem 3, let p be a prime and a positive integer. Then phi of p raised to a is equal to p raised to a minus p raised to a minus 1 is equal to p raised to a minus 1. So we have the example. Let our p is equal to 6 and our a is equal to 4. So phi of 6 raised to 4 is equal to 6 raised to 4 minus 6 raised to 3. So dili pasabot nga dili ta mo follow sa rules of exponent katong pwede lang siya i-minus kung pareha og base. Kana dili gid siya kailangan nimo siya kuhaan gid ang answer. Kung 6 raised to 4, so 6 times 6 times 6 times 6 is equal to 1,296. Minus to 6 raised to 3 or 6 times 6 times 6 is equal to 216. So 1,296 minus 216, we have 1,080. So the phi of 6 raised to 4 is equal to 1,080. So let's have the another example of number 2. So phi raised to 8 minus 5, or p is 8 and 5 is 8. So 8 raised to 5 minus 8 raised to 4. Same process. 8 times 8 times 8 times 8 times 8 is equal to 32,768 minus 8 raised to 4, or 8 times 8 times 8 times 8 is equal to 4,096. Then let us subtract 32,768 minus 4,096 is equal to 28,672. To explain this, these positive integers is less than p raised to a that are not relatively prime to p are those integers that not exceeding p raised to a. That are divisible by p. There are exactly p raised to a minus 1 such integers. So there are p raised to a minus p raised to a minus 1 integers that less than p raised to a that are relatively prime to p raised to a. So therefore, the phi of p raised to a is equal to p raised to a minus p raised to a minus 1. And next we have the theorem 4. So let m and n be relatively prime positive integers, then phi of mn is equal to phi of m times phi of n, where m and n are the greatest common divisors. These theorems is similar to the arithmetic functions that we have discussed earlier. So they are just the same theorem. And we have the theorem number 5. So theorem number 5, let n is equal to p sub 1 raised to a sub 1, p sub 2 raised to a sub 2, all the way to the p sub k raised to a sub k, be the prime factorization of the positive integer n. Then the phi of n is equal to n, close and open parenthesis, 1 minus 1 over p sub 1, multiplies to 1 minus 1 over p sub 2, all the way to 1 minus 1 over p sub k. So before we explain that formula, the formula, so let's have the example. So let's say that our n is 100. So phi of 100. Since 100 is factorable, so we have p of 100 is equal to phi of 2 squared, 5 squared. Or 2 times 2 is 4, then 5 times 5 is 25. Then 25 times 4 is 100. So let is equal to 100. Then our p sub 1 here is 2. So 1 minus 1 half, close and open parenthesis, 1 minus 1 fifth, or our second prime is 5, 1 minus 1 fifth. Therefore, next, bring down 100, then 1 half, because 1 minus 1 half is 1 half, then 1 minus 1 fifth is 4 fifth. So 100 times 1 half times 4 fifth is 4 over 10, because 1 times 4 is 4, 2 times 5 is 10. Then 100 times 4 is 400 over 10, then 400 divided 10 is 40. So therefore, the phi of 100 is 40. So to understand more, since our phi is a multiplicative, then we know that the theorem 1 tells us that if a prime power factorizations of n is equal to p sub 1 raised to a sub 1, then p sub 2 raised to a sub 2, all the way to the p sub k raised to a sub k, then we have the phi of n is equal to phi of p sub 1 raised to a sub 1 multiplies to p sub 2 raised to a sub 2, all the way to the phi of p sub k raised to a sub k. And we also apply the theorem 3, and it says that the phi of p sub j raised to a sub j is equal to p sub j raised to a sub j minus p sub j raised to a minus 1 is equal to p sub j raised to a sub j. 1 multiplies to 1 minus 1 over p sub j. For j is equal to 1, 2, dot, 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 and k. Hence, that our phi of n is equal to p sub 1 raised to a sub 1, quantity of 1 minus 1 over p sub 1, then multiplies to phi sub 2 raised to a sub 2, quantity of 1 minus 1 over p sub 2, all the way to the p sub k raised to a sub k, multiplies to the quantity of 1 minus 1 over p sub k, and it is equal to p sub 1 raised to a sub 1, p sub 2 is raised sub 2, all the way to the p sub k raised to a sub k, quantity of 1 minus 1 over p sub 1 multiplies to the quantity of 1 minus 1 over p sub 2, all the way to the quantity of 1 minus 1 over p sub k, and is equal to n is equal to 1 minus 1 p sub 1 multiplies to 1 minus 1 over p sub 2, all the way to the 1 minus 1 over p sub k. And this theorem 5, it simply reminds us that tells that the theorem 1 is a prime power factorization, and theorem 1 and theorem 3 applies in this theorem 5. So in other words, this desired formula for phi of n. And now we are in the theorem 6. So let n be a positive integer. Then the summation of d over n, phi of d is equal to n. So before we proceed before we discuss that, before we tell that proof, let's have the example. So let's say that we have the prime numbers, we have the number 12. So we know that the divisors of 12 are 1, 2, 3, 4, 6, and 12. So there are two chance for these divisors of 12 are 1, 1, 2, 2, 2, and 4, which is sum up to 12. Because 1 plus 1, 2, 2 plus 2, 4, 2 plus 2, 4 plus 2 is 6, 6 plus 2 is 8, 8 plus 4 is 12. So to explain more than that, so the functions f of n is equal to 1 is totally a multiplicative. So let d of n be the number of divisors of n. Then since d of n is equal to summation of d over n 1, we see that d of n is a multiplicative. So this functions f of n is equal to n is totally a multiplicative. So let the summation of n be the sum of divisors of n. Since the summations of n is equal to summation of d of n, and we see that the summation of n is multiplicative. In general, we can apply this trick to any power of n. So to prove another proof that statement, so we split the set of integers from 1 to n into classes. Put the integers m into the class of c sub d if the greatest common divisor of n and n is d. And when we set that m is in CD example, that the GCD is m of n is equal to d. And if and only if that the m of d and n of d is equal to 1. Hence, that the numbers of integers that c sub d is the number of the positive integers not exceeding to n over d that are relatively prime to the integers n of d from this. So consistently say that the n of summation of n is equal to summation of d over n phi of n over d, as d runs through the positive integers that divide n, or n of d also runs through this divisor, so that the n is summation of d over n phi of n over d is equal to the summation of d over n phi over d. So kani siya nga theorem, kani siya nga explanations is mo ni siyang let n be a positive integer, then the phi the summation of d over n phi of d is equal to n. So that's how theorem 6 tells us. So let us just know that d of n it is a multiplicative, then f of n is also a multiplicative, sum of n is also multiplicative. So we just apply this in any power of n, the sum and the number of divisor. So when we say the sum of divisors functions, it is denoted by the sum of n is the sum of all the positive divisors of n. So let us example, the phi of 12 is equal to, we know that the divisors of 12 are 1, 2, 3, 4, 6, and 12. And we find the sum of phi of sum of n or sum of 12, it will results to 28. We note that we can express the sum of n as sum of n is equal to the summation of d over n d. Now let us try to prove that the summation of n is a multiplicative functions. So the sum of divisors functions, the sum of the divisors functions or sum of n is multiplicative. We prove that the theorem 1 says that the summatory functions is multiplicative once f is multiplicative. Thus, let f of n is equal to n. And notice that f of n is multiplicative. As a result, the sum of n is multiplicative. And we also found out that the sum of n is multiplicative if it remains to evaluate the sum of n at powers of primes, and hence we can derive a formula for its values at any positive integers. So let p be a prime and let n is equal to p sub 1 raised to a sub 1, p sub 2 raised to a sub 2, all the way to the p sub t raised to a sub t, be sum of p sub a is equal to p raised to a plus 1 minus 1 over p minus 1. And as a result, and it will result to the sum of n is equal to summation of j is equal to 1 to t, or p sub j raised to a sub g plus 1 minus 1 over p sub j minus 1. And notice that the divisors of p sub a are 1 and p sub 2 all the way to p sub a. Thus, a summation of p sub a is equal to 1 plus p sub 2 plus ... and plus p sub a is equal to p sub 1 p raised to a plus 1 minus 1 over p minus 1, where the above sum is the sum of the terms of the geometric progressions. Now, since our sum of n is a multiplicative, we have the sum of n is equal to sum of p raised to a sub 1 multiplied to the sum of p raised to a sub 2 all the way to the sum of p raised to a sub t is equal to p sub 1 raised to a sub 1 plus 1 minus 1 over p sub 1 minus 1 minus p sub 2 raised to a sub 2 plus 1 minus 1 over p sub 2 minus 1 all the way to the p sub t raised to a sub t plus 1 minus 1 over p sub t minus 1, and 2, the summation of g is equal to 1 to t is results to p sub g raised to a sub g plus 1 minus 1 over p sub g minus 1. And let us have the example. Our n is 200. Let us find the sum of 200. Sum of 200 is equal to sum of 2 raised to 3, 5 raised to 2, and is equal to 2 raised to 4 minus 1 over 2 minus 1, then 5 raised to 3 minus 1, then 5 raised to 1 is equal to 15.31, and is equal to the sum of 200 is 465. The number of divisors functions. The number of divisors functions is denoted by the tau of n, which is the sum of all the positive divisors of n. So let us have the example. Let n is equal to 8. So the tau of 8 is equal to the sum of 4. So the tau of 8 is equal to the sum of 4. And we can also express the tau of n as tau of n is equal to summation of d of n 1. We can also prove that the tau of n is a multiplicative function, which is the number of divisors functions tau of n is multiplicative. With a theorem, we say that f of n is equal to 1, therefore tau of n is multiplicative. We also find a formula that evaluates tau of n for any integer n. So let's say that p be a prime and let n is equal to p sub 1 raised to a sub 1, p sub 2 raised to a sub 2, all the way to the p sub t raised to a sub t be a positive integer. Then tau of p sub a is equal to a sub a plus 1, and as a result, the tau of n is equal to g is equal to 1 all the way to t multiplies to a sub g plus 1. The divisors p sub a, as I mentioned before, are 1, p, p sub 2, p sub a. Thus, tau of p sub a is equal to a plus 1. Now, since the tau of n is multiplicative, we have the tau of n is equal to tau of p raised to a sub 1 multiplied to the tau of p raised to a sub 2 all the way to the tau of p raised to a sub t and is equal to a sub 1 plus 1, a sub 2 plus 1 all the way to the a sub t plus 1, and is equal to j is equal to 1 all the way to t, then a j plus 1. So let us try to find the tau of 200. We have the example. So the tau of 200 is 2 raised to 3, 5 raised to 2. So it's equal to 3 plus 1, because 3 plus 1, then 2 plus 1. So 3 plus 1 is 4, then 2 plus 1 is 3. 4 times 3 is 12. So the tau of 200 is 12. We have the statistical problem. And let's suppose that a group of Serenio conduct a study entitled The Correlation Between Arm Span and Foot Length of BS Ed Mathematics ADN 3 students of Davao Oriental State University. And one of their objectives is to find the relationship between the two variables. Below is the data that they have gathered. So as you can see in the data, we have arm span and foot length, and it is in a table form. So total respondents for this is 27. So we have arm span for arm span we have 27 respondents, and foot and we have 27 respondents. And as you can see, the table 1, it is a measurement of the arm span and foot length. So the mean of the arm span is 156 centimeter, while the mean of the foot length is 23 centimeter. So to find its relationship between the two variables, using the Pearson correlation coefficient, we can find the relationship between the two variables. So as you can see in the link for the Pearson correlation coefficient. So this is the link for the Pearson correlation coefficient. And using this, we solve this through the use of technology, use of the ICT tools, and this link is this link provided is the Pearson correlation coefficient. So as you can see in the table, the correlation between the arm span and foot length, we say that our value is 0.5057 10,000th, and our p-value is 0.007. And to interpret this, and we set our significance level to 500s, and let's say that the results is significant at p is greater than the 500s and moderate positive relationship. So as you can see in the table, to conclude this, the table 2 shows that the relationship between the arm span and the foot length. The R value results to 0.05057 10,000s with the probability of P is equal to 0.7 thousandths or significant. This study implies that the two variables, which are arm span and foot length, are positively correlated. And thank you so much for your watching. I hope you learned something today. Thank you so much. Have a good day.